The Large Magellanic Cloud, 170,000 light-years away and the nearest galaxy to our own. It contains 10 billion stars. February 23rd, 1987, a tank of water a mile underground in Ohio. A stream of high-energy particles, which has taken 170,000 years to reach Earth, zips through the tank and the Earth in a fraction of a second. At the time, no one notices. The following night in New Zealand, Albert Jones, an amateur astronomer, is observing the Large Magellanic Cloud. He can scarcely believe his eyes, because in the middle of the familiar galaxy is a bright new point of light. He thinks it must be a supernova, the explosive death of a giant star. But no such event has been visible with the naked eye for the past 400 years. His first priority is to alert other astronomers.
And I've been looking at the Magellanic Cloud, and I've been looking in the region of HDE 269858 here, and there's quite a bright blue star quite near.
2 hours later, his message reaches Rob McNaught in New South Wales. McNaught is a professional astronomer working with a satellite tracking telescope. With this, he photographs a Large Magellanic Cloud, and by checking against earlier pictures of the same galaxy, confirms what Jones had suspected: a supernova. Minutes later, news of the discovery is winging its way all around the world. Soon, hundreds of telescopes are focusing the light from a distant star that died explosively. So far away that what they are now seeing actually happened 170,000 years ago. It has taken that long for the light to reach the Earth. The sudden death of a star in a supernova explosion is one of the most dramatic and powerful events in the universe. And however distant, it's rather frightening, because it reminds us that nothing, not even the star that is our sun, will last forever. Because one day the sun must die, not with a bang, but like the vast majority of other stars, with a whimper. But a whimper to a body as big as the sun is an unparalleled catastrophe to a planet as fragile as the Earth. And one day, 5 billion years on in the future, our sun will start to change. There will be one last perfect sunset. And then the sun will swell, parching the Earth and boiling away the oceans. There's no escaping the sun's fate. Death is inevitable for the sun, just as it is for you and me. It will come when the sun finally runs out of fuel at the end of a long, long life of around 10 billion years. But when it dies, the sun won't just shrivel up. Changes in its interior will make the sun's outer layers billow out like a hot air balloon. As it swells, the sun will first swallow up Mercury, then Venus, and even perhaps the Earth itself. It will only take a few million years for the dying sun to become a red giant, a cool, bloated object swollen to 100 times its previous size. 70 years ago, astronomers had no idea how stars lived and died, and so the discovery of giant stars came as a shock to everyone. At that time, this historic telescope, the 100-inch diameter reflecting telescope on Mount Wilson on a hillside above Los Angeles, was the biggest in the world. But even so, its 8-foot diameter mirror couldn't show a star as anything but a speck of light. But the great physicist Albert Michelson had big ideas. He constructed a periscope arrangement across the top of the telescope, which increased its power. And by doing this, he was able to measure the physical size of a star for the first time. The star he chose was Betelgeuse, one of the closest red giant stars in the sky. Betelgeuse turned out to be 700 million miles across, so vast that you could fit 400 million of our sun inside it. The discovery of Betelgeuse's immense size came as such a surprise that it even made the front page of the New York Times. Most nights you can pick out a handful of red giants in the sky. Aldebaran, in Taurus, is 50 times wider than the Sun, itself almost 1 million miles across. One of the reddest stars in the sky is Antares in Scorpius, 300 times bigger than the Sun. And Mira, in Cetus, is 350 times the Sun's size. Even so, none of these stars is nearly as big as Betelgeuse, which, if placed in the Sun's position, would stretch almost as far out as Jupiter. But a red giant is all show and no substance, a bit like a lump of cosmic candy floss. It has virtually no control over its swollen atmosphere. As the months go by, the star swells and shrinks, changing visibly in brightness as it does so. As time passes, the red giant becomes more and more unstable. Finally, it gently puffs its distended atmosphere away into space. For a moment in the star's life, equivalent to the last 30 minutes in a human life of 70 years, the old star's fading core is surrounded by a smoke ring of its former atmosphere. And soon this too will be gone. And that's how our sun will die, an event no more important to the universe than the snuffing out of a candle to us. But a few very rare stars, the heaviest and most brilliant of all, make sure that their deaths are not overlooked. These stars die as they've lived, indulging in excess all the way to the end. When a star like this has to go, it does it young and with a bang, as a supernova. The Chinese of 2,000 years ago were fascinated by supernovae. They call them guest stars. They took great care to log the position of these new stars when they appeared. To the Chinese, they were vital astrological signs. One record reports the following. A guest star appeared within Nanmen. It was as large as half a mat. It showed 5 colors and it scintillated. It gradually became smaller and disappeared. According to the standard prognostication, this means insurrection. 1400 years later, the constellation of Cassiopeia was completely altered by the appearance of a brilliant supernova. On November the 6th, 1572. One eyewitness was Tycho Brahe, 16th century nobleman, astronomer, and possessor of a golden nose, a precious replacement for his original nose, which he lost in a duel. He reported the following. A little before dinner, I was returning to the house, when, behold, directly overhead, a certain strange star was suddenly seen, flashing its light with a radiant gleam. I satisfied myself that no star of that kind had ever shone forth before. Tycho's supernova of 1572 shone as brilliantly as the planet Venus, 40 times brighter than the brightest stars in the sky. It was followed just 30 years later by another that was only a little less brilliant. One that was observed carefully by Tycho's assistant, Johannes Kepler. Kepler's supernova was seen in the constellation of Ophiuchus, the serpent bearer. But since Tycho's and Kepler's supernovae, there have been none seen in our galaxy, a city of 200 billion stars. None of them seems ready to turn into a supernova just yet. Our galaxy, though, is just one amongst millions of star cities in the universe. Supernovae can flare up in these other galaxies too. And if you have a telescope, you may be able to find your very own supernova. The Reverend Robert Evans has 2 quite separate heavenly connections. The first is his responsibility for his Christian flock in Hazelbrook, New South Wales. and the second is his unrivaled record in discovering distant supernovae. His passion for the heavens started when he was just a young boy.
My father had learned a little tiny bit about astronomy from being in the Scouts, and he brought home a star atlas and a pair of binoculars and showed me where Orion was and a few other objects, and I slowly learned different objects in the sky. And then, of course, as time went by, I made or bought telescopes of different sizes. The first one was made from a spectacle lens that my brother got, and a microscope eyepiece and 2 rolls of paper and some cardboard. So that was my first attempt to have a telescope.
Bob started hunting for supernovae in the 1950s, when supernovae were only picked up by professional astronomers using large telescopes. But Bob persevered. He steadily improved his technique and his telescope, and in 1980 he discovered his first supernova. Still, with no more than a backyard telescope, Bob has outclassed all the professionals by finding 17 new supernovae. Why has he been so successful?
You don't find things in the universe, such as supernovae in distant galaxies, unless you actually look for them. And one of the reasons why I've been successful is that I've done a lot of looking. I've also done things to increase the possibilities of finding a supernova, such as developing the number of galaxies that I look at until there's a fairly high number. I suppose I look at about 14 or 1500 different galaxies during a year. I have tried to memorise the appearance of many of these galaxies so that I can recognise instantly any unusual feature. And when that happens, it's necessary to have materials at hand which can be used to verify whether it is a new object or not that's been found. Actually, I don't think that what I can do is different from what a lot of people could do. Most people can remember pretty well hundreds and hundreds of different faces of their friends and relatives, and they could recognise them at any time, and these galaxies are my friends. There are various things that happen with all of the different discoveries. One of the things that happened with the Centaurus A supernova was that David Malan had a night on the Anglo-Australian telescope about a week after, or several weeks after the supernova reached maximum brightness. And 6 months previously they had decided to photograph Centaurus A in order to look for globular clusters in this galaxy, which perhaps is 10 million light years away. It turned out to be a perfect night with very tiny star images, and so pretty well the best photograph that's ever been taken of that galaxy has got this supernova bang in the middle of it.
Lift up your voices, rejoice again, I say, rejoice.
And when Bob discovers a supernova with his backyard telescope, the professionals really get cracking. Using huge telescopes like the Anglo-Australian telescope in the dome behind me, they've been able to study Bob's exploding stars and work out just what it is that makes them go with a bang. A supergiant star destined to go supernova begins producing power in its core by turning hydrogen into helium. But unlike other stars, the star can carry on even when all the hydrogen is used up. Its gravity is so strong that it can fuse helium into carbon, a new source of power to keep the star shining. If the star is massive enough, it can still go on by turning carbon into neon. The star is realizing the old alchemist dream of changing one substance into another, continuously creating new elements to keep on shining. But this can only go so far. In the final stage, neon burns to silicon, and when this is all used up, silicon burns to iron. But that is the end of the road. Iron fusion requires energy to be put in rather than causing it to be given out. And the only way the star can do this is to shrink its core just that little bit more. But that turns up the temperature to 50,000 million degrees, and it also causes the pressure to increase as well. It's just too much for a poor star to take. And deep down in the star's core, the iron atoms begin to smash together. In less than 1 second, the star's core catastrophically collapses. The shock of this collapse triggers an immense surge of energy, causing most of the star to lift off into space in one of the most awesome acts of violence in the universe. An inferno which creates elements even heavier than iron. But astronomers have calculated that even before a star blows up, you should be able to pick up its distress signals. What happens is that tiny particles called neutrinos escape from the collapsing core at the speed of light. But you can't pick them up with a conventional telescope like that one. What you need, bizarre though it may seem, is a tank of water about a mile underground. Shielded from stray radiation by the overlying rock, scientists have built a neutrino telescope, a huge swimming pool deep down an old salt mine in Ohio. At 7 hours, 35 minutes and 41 seconds on the morning of February 23rd, 1987, this vast pool of water was disturbed by a burst of neutrinos from space. The burst lasted for only 12 seconds. The neutrinos had traveled from a distant star immediately before it exploded as a supernova. They went unnoticed at the time because the scientists didn't carry out their routine checks of the neutrino records until later. And so, when Albert Jones and other astronomers around the world turned their telescopes towards the Large Magellanic Cloud on the following evening, the sighting of the nearest supernova for 400 years came as a complete surprise.
And I turned the telescope towards the Magellanic Cloud, and there was something in this field of view that wasn't there the night before. But goodness gracious me, this is something unusual. A bright blue star. Have I got into the right region, you see? So I checked, no, it was the right region. And so I quickly marked it down on the chart. I have a chart, you see, I marked it down on the chart where it was. And I was going to make an estimate of its brightness by comparing it with the stars around it, you see. Find a star that's a wee bit brighter, another that's a little bit fainter, and then I'd get just the right brightness of the star. But the clouds beat me to it, so I waited and waited and waited for about half an hour, and I was hoping it would clear up, and it did. The clouds went away, and I got the comparison stars, and I got a good brightness. Went back to the phone and told Frank Bateson it's magnitude 4.9. So he got onto the phone then, and he phoned the big observatory in Siding Springs in Australia.
At Siding Spring, astronomer Rob McNaught uses a special photographic telescope to track and measure the orbits of man-made satellites.
Hello? A supernova?
He was working in his office checking his satellite data when he received the message about the supernova.
I rushed out in a state of shock and excitement and looked up, and sure enough, there was a bright supernova in the Magellanic Cloud. It was just visible to the naked eye. I knew it was many centuries since the last naked eye supernova, and if it did turn out to be a supernova, which at that time we weren't certain about, I knew that the astronomical community would be falling over themselves to study it. And since supernovae were recognized as one of the most exotic phenomena in the universe only around 50 years ago, this was the first bright supernova that allowed them to actually study in great detail what up until this time had been largely theory. So I took a photograph with the satellite camera. So from the photograph, I measured the position and then looked at old photographs, and sure enough, there was a faint star in just the same position as the supernova. Subsequent to that, I phoned the information through to Boston, Massachusetts, where there is the Central Bureau for Astronomical Telegrams, who make announcements of astronomical discoveries to the astronomical community. They didn't at that time have an accurate position or an identification for the supernova.
The star which went up, known as Sanduliac minus 69 degrees 202, was a brilliant supergiant star 100,000 times brighter than our sun. It exploded with the brilliance of 250 million suns and its gases sped from the wreckage at 40 million miles an hour. The radioactive decay of the new elements born in the heat and chaos of the explosion kept the supernova burning brightly long after its outburst. It was 4 months before this cosmic atom bomb started to fade from sight. But the supernova may have packed an unexpected punch. Astronomers have worked out that the blast from the supernova sent a small shockwave through the Earth's atmosphere, even though it was 170,000 light-years away. So imagine what might happen if a supernova were to explode closer to home, within our own galaxy. What kind of effects would this have on the Earth? Well, if a supernova went off within 100 light-years of the Earth, life would certainly be put at risk. The blast from the supernova would damage our sunscreen, the ozone layer, and that would let all the dangerous high-energy radiation through. At best, this would cause mutations in plants and animals amongst their cells. At worst, life would be completely eradicated. You'll be pleased to hear that there are no supernova candidates, though, within 100 light-years of the Earth. My prime tip, though, for the next supernova is a star called Eta Carina. Although it's 9,000 light-years away, it's 5 million times brighter than the Sun, and it's burning its fuel at a fantastic rate. When it goes supernova, in perhaps a few centuries' time, it'll outshine everything else in our skies except the Sun and the Moon. But supernovae aren't all doom and destruction. In fact, they're the first step on the road to star birth. Thousands of years after the supernova explosion, when things have had a chance to cool down, the products of the outburst are still expanding into space as a supernova remnant, a great cosmic bubble. The expanding remnant rams into the thinly spread gas and dust between the surrounding stars. As millions of years go by, the scooped-up gas becomes more and more densely packed, eventually becoming dense enough to collapse and give birth to new stars. But supernovae do more than trigger starbirth. They also seed space with new, more complex materials with which to build planets and life. In this photograph of a supernova remnant, oxygen shines green, hydrogen shines blue, while sulfur shines red. In these remnants, too, are the much rarer heavy elements briefly synthesized in the heat and fury of the outburst, such as gold, platinum, and silver. The proof that they synthesize heavy elements comes from meteorites, or what some people call shooting stars, as they travel through the Earth's atmosphere. In actual fact, they're rocks from space, like this one here that fell quite close to here in Australia about 100 years ago. Meteorites like this contain unmistakable traces of radioactive elements that could only have been produced in supernovae. But ultimately, you and I owe our entire existence to supernovae. In the beginning, in the first generation of stars, there were no complex elements, just hydrogen and helium. Nowhere in the universe was the matter we have around us today, like the carbon making up the trees, the gold and silver in the Earth's crust, and also the rich mix of matter making up our bodies. All of this came from generations of stars that exploded as supernovae. Stardoom, looked at in the long term, is temporary. It is just one step in the continuous cycle of birth, life, and death that operates throughout the universe. From a supernova's funeral pyre come the heavy elements needed for the later creation of planets like Earth, and of life itself. We were born from stars. We are stardust. Supernova explosions were essential in the creation of mankind.